Hello everyone, today I'm going to deliver another lecture on material nonlinearity, plastic movement, plastic hinge and ultimate load. So structural analysis of material nonlinearity, plastic movement and plastic hinge and ultimate load for beam and frames. The course content will be included. First of all, I will explain the material non-linearity, concrete, steel and reinforced concrete, and then analysis of linear elastic and inelastic system, and showing some math example of plastic moment for beam. And then I will show another part, which is the plastic moment of typical section and plastic hinge and ultimate load. And mostly I will show the math example of material non-linearity and plastic moment of for the beam and frame. Okay, let's start some theory. Okay, material non-linearity we have shown here. I'm going to here. Uh, this lecture sheet is taken from Professor Dr. Iftikhar Anam sir, University of Asia Pacific. Okay, the material nonlinearity and plastic moment. As the mentioned in previous section, the structural properties cannot be assumed remain constant in many practical situations. In addition to geometric nonlinearity that lead to instability of structure with the linear properties of linear material properties, and the variation of material properties itself in it may take the structural analysis non-linear. For example, yielding of structural materials like situation in a severe loading condition or ground vibration may alter alter the stiffness properties, which need to update it in structural deformation. Okay, let's show another, which material non-linearity in concrete, steel and uh, um, reinforced concrete. The concrete and steel are the most common among the structural materials in civil engineering construction. Among them, the concrete is most stronger compression in than in tension or tensile strength of in order to 1/10 of the compressive strength. While the tensile stress relationship almost linear and stress strain relationship is compression for non-linear in the beginning figure we have been shown here. Okay, so the steel on the other hand, the similar stress strain properties, tension compression after the initial linear elastic portion, the stress remain almost constant while the strain increase significantly. This is typically followed by the some increase stress at the reducing elasticity and finally decrease the stress leading to buckle of the specimen. Okay, we have been seeing the reinforcement concrete or RC in unique combination of these two material where the complexity of their consecutive behavior into effect. The behavior of RC cannot be modeled by properly by linear elastic behavior. Recognizing that the design of RC structure has gradually shifted over the year from the elastic working stress design to the more rational ultimate strength design. The design of the steel structure has also undergone similar transition from allowable stress design ASD method to the load resistant factor design method. Okay, we've been seen here figure 1, the stress strain model in concrete is compression. We've been seen x-axis is strain and y-axis is stress, and this is the parabolic and this is the straight line. Here is the concrete axis is strain, and y-axis is stress, and the line is parabola and straight line. This is the after the inot it will be straight line. And another one we have been seeing typically strain for steel axis is strain, y axis is the stress, and typically stress versus strain here, and this is the ultimate stress, and this is the breaking point, and this is the perfectly plastic model. So here is the elastic perfectly plastic model. Still strain is x axis, y axis is stress, and this slope is the modulus of elasticity, and this is the plastic, and this is the ultimate, and this is the breaking point. Okay. um, Now we can see the plastic moment and typical section. These are the completed. Now we can see analysis of linear elastic and inelastic system. Okay, here's the analysis of a linearly elastic and inelastic system. For the linear elastic system, for the relation between applied force Fs in the resulting deformation is linear, as we know, stress equal to F equal to Ku, where K is the linear stiffness for its unit force length. And another expression we have been the resisting force can be Fs equal to Fs equal to, and this is called the inelastic dynamic system. And structural analysis such a system can only perform in iterative method. Okay, these are also completed, and now we can see another, which is the plastic moment and typical section. And the iterative method recognize analyze the non-linear system is quite laborious and time consuming in convergence to exact solution is not always granted. It is usually followed by the typical structural analysis for very important project. However, the calculation of the ultimate moment capacity of cross-sectional ultimate load carrying capacity structure usually much simpler and more stress to the structural designer. The following example of the ultimate moment capacity optically steel and RC section. Okay, let's see. We have been seen here. This is the stress of A60 KSI, and this is the plastic elastic condition. After the load is increasing, the condition will be fully plastic, and when the plastic is arise, then we have been found the compression zone Fy by 2, and compression tensile zone also Fy into A by 2, and the distance between compression and tension will be T. The plastic moment we have been shown here. Stress, we know stress My by mc by I. So if we take the mc is here, and stress y into I by c. I by c is a section modulus. Here is a section, and My is the elastic moment. The same, the plastic moment mc equal to c into d, as we know, c into d here, and c means it will be t into d. We can see we can take the c mean compression, t is the tension. So Fy, as we will know, Fy A by 2 into d, A by into d, A by 2 into d, we can call the section modulus Z, plastic section modulus, and stress into Z. Okay, so the value will be MP greater than must be My, or yielding. So we have been shown here, the beam is when the load is applied, the bending will be buckled like this. So this will be My, or elastic moment, and this will be plastic moment. That's why plastic moment will be always be greater than elastic moment. Okay, now now we'll see the math example of plastic moment of beam. Here is the find the My yielding moment, section modulus M and Z, where the stress is given 60 KSI. So these are the section is given, B is 10 and height is 12, and distance between B and D you have to find out, and these are the half portion A by 2, and the last portion we've been seen A by 2, and all the section is steel. Now we can see, now we have been find out the moment of inertia. As we know, B d cube by 12, B is 10, here is a 10, and D, we know that uh, D is 12, here is a D, and 12, and founding this value. A, we know the value of A is given to 12 into 10, here is a 12 into 10, and C will be D by 2. As we know the D, how we will calculate D? This is the depth of D, and D by 2 will be 6. And what will be the value of D? Value of D will be this 6 divided by 2 is 3, and another 6 divided by 2 is 3. See, 3 plus 3 is 6. So this is the very important to find out the D. I'll show again and again. So My will be stress into I by C, which is found 1200 cubic feet, and MP equal to stress A by 2 into D, and found 1800. So we can say MP is greater than My. So it will so it's okay. So what is the D? D is distance between CG of two area. Okay, let's see another example, which is find out the yielding moment, plastic moment, section modulus jet, and when stress is given 60 ksi. So we have been seen here, the section is given here. So we will calculate the CG of Y, which is AY A1 Y1. So A1 is 12 into 2. This is the A1. Y1 is 12. Here, this is the 12. 6 into 6 equal to 12 divided by 2. And another one, A2 Y2. This is the A into 12 into 2. A2 Y2. Y2 means 12 plus 2 divided by 2. A2 Y2 divided by A1, which is 12 into 2, and A2 12 into 2, and found 9.5 from bottom. Now we can see here that 12 plus 2. This is the 12 plus 2 minus 9.5, which is, we can say, is 4.5. So as we've been found two value, which is 9.5, and another one is 4.5. So we're taking them always the bigger value, which is 9.5, because we will reduce the section modulus S. So moment of inertia as it is, as we have been shown, this is the 1, and Pt cube by 12, B is 2 and D is 12, B is 2 and D is 12, and divided by 12, and plus 24. 24 is area into C minus 6. As we know, this is the CG 6 minus CG is 9, and founding in this way, founding this below. Here, as the total area is 48 and A by 2 is 12. Now we can calculate 2 into x. This is the 2 into x, and another was is 12, and then we can find x equal to 6. We can calculate D1 A1 Y1 plus A1, and finding 3, and D2 I will calculate A2 Y2 plus A3 Y3 divided by A plus A2 plus S3, and found 11.67. So as we have been found total here 11.67, and the minus from 3. This is the 3, and then we will found the value of D. D means distance between 2 CG. The distance between 2 CG, it will be 8.67. Now we can calculate the yielding moment Mi into S, or I by C, founding 5538, and MP found F stress into Z, or A by 2 into D, and found 12485. So you can see the plastic moment is greater than yielding moment, so it is okay. Now you can see calculate the plastic moment and yielding moment of the given section below. So we've been seen here that all the section is below. We've been found 12 into 2. So this is the 12 into 2 plus 10 into 2. This is the 10. The distance is given 10 into 2 is the flange or web thickness, and 20 into here. This is the 20 into 1.5, and found 74. A by 2 will be 37. So now we can 20 into 1.5, 2 into 1.5, 2 into x. This is the 2 into x, it will be 37. This is the 37, and found x equal to 3.7. And D1 A1, calculate the D1. How will calculate A1 Y1 plus A2 Y2 divided by A1 plus A2, and found 1.22. The same way D2 will founding A2 Y2 plus A3 Y3 divided by A2 plus A3, and finding 11. Now we can calculate the D. How will calculate D? Total D been found. Here the 11. This is the 11, and another CG we have been found 9.7. So if we If we deduct 11 minus 1.22 uh, and found 9.78. I will calculate yeah, y bar and found 6.67. So we've been seen after the putting this below y minus d, which is 7.4. 7.4 is greater than, so we'll take the bigger below. After now we'll calculate the moment of inertia and putting this value for yielding we have been found 1367 kip and plastic we have been found 1809 kip. So these are the bigger than this, so we can say these are the okay. Now this portion math example has ended. Now we can see the plastic moment of typical section. This also completed. Now we can see the plastic hinge and ultimate load. So okay, before going to here, I want to say another math example here. So, another example. I'll calculate the ultimate moment capacity of RC section is shown below. Is apparently and Fy is given here. So as we know, the B is given to 20 and D is 15.5 and A steel area is 3 steel area found here, and A as Fy 0.853 efficiency into B found 3.46 and moment ultimate as Fyt minus Fyt found 1642. Okay, now we can see here plastic hinge and ultimate load. Here the ultimate load and simple beam, plastic hinge and ultimate load. Since the plastic moment of the section is ultimate moment capacity, it can not take any more moment beyond this, as such as the section behave almost the eternal hinge within structure, such as hypothetical internal hinge is called plastic hinge. By adding new equation of status, it reduced by 1 degree of structural indeterminacy structure, and therefore uniform information such as hinge can take the structural statically indeterminate and eventually lead the instability which can causes the ultimate load collapse structure and formation of collapse mechanism. Okay, by calculating the structural load necessary such the hinge is possible, if possible, to calculate some needed to from collapse mechanism of structure, and this load can called the ultimate load of structure, and it is important to design because it provides the information about the load of the structure can possibly sustain to demonstrate by the following example. Okay, before I'm going to example, I wanna say here calculate the ultimate load capacity of the simple supported beam is shown here. So before I'm going to here, I wanna say here. So you can see here ultimate at plastic one as the simple supported beam, the maximum moment will be WL square by 8. So point B will be failed because there is a maximum moment. So dou C is unknown minus equation. Dou C, we can see in this criteria there will be maximum moment is here and maximum moment is here. So we can see point A and point D, the structure will be either point A or either point D, as there is a maximum moment. Where the maximum moment structure will be failed here. Okay, so we can see here dou C unknown minus equation is 1 minus unstable. Here the another dou C unknown support minus equation is 2, this is stable. Okay, we've been seen here is a fixed support and the ruler support. So plastic moment will be the moment diagram will be like this. So we can say the maximum moment will be here or here. So these are the two hinges will be created at the maximum point, and structure will be fail either this point or this point. So in this case we have been seeing the two support are fixed support, so the member bending moment diagram will be like this, and maximum bending will be found either here or here or here. So the maximum moment is found in here. That's why the structure will be either fail will be in either here or here or here. So you cannot see here. So you can say the only three uh, portion will be failed. Okay, so you can see here ultimate load capacity when the load is P. So you can see this is the you have to memorize some formula. When the simple supported and the axial load will be P, then moment will be PL by 4. So PL by 4, if we change here, then ultimate load will be 4 MP divided by L. The same as the simple supported beam. If the UDL load, then WL square by 8, the maximum moment WL square by 8, WL square by 8, and W will be 4 8 MP into L square. When the support is changed from hinge or ruler to fixed, then it will be PL by 8, and on the simple support that was a PL by 4, but in the fixed support PL by 8. Okay, so the maximum moment PL by 8, and here PL by 8, PL by 8, so MP equal to PL by 8, and ultimate load is 4 MP by 8. But noted that here is a 3 maximum moment we have been found. So if in this case the structure will be failed either this portion, this, or this here. Okay, we have been seeing another structure which is fixed support, but load is UDL, which is L by 2, L by 2. So there will be WL square by 24, and this portion will be WL square by 12. This also 12. So if we consider here like this, the total will be WL square by 8, but here by 24, and this is by 12. If we calculate, the total will be WL square by 8. So in this case we have been seen here 2 MP equal to WL square by 8. Why 2 MP? As we know, total WL square by 8, that means these are the MP and these are the MP. So that's why 2 MP. 2 MP WL square by 8. So if we W is taking here, then we will be 8 into 2, that will be 16 MP by L square. Okay, another one we've been seen here the load is P, the cantilever beam W L by 2, L by 2, and the bending moment PL by 8, and founding this, and cantilever and UDL load, and founding this way. So we have been seeing various moment formula. One load is diagram is PL by 4 and PL by 8, PL by 8, and this is the we have to taking memorize, and the pin support and fixed support WL square by 11.67, and this is WL square by 16, PL by PL, and WL square by 2. Okay, this was 16. Okay, let's see here the ultimate plastic and ultimate load is at the inlet. Now we can see another topic, energy formulation of collapse mechanism. The calculation of the ultimate load capacity based on the bending moment diagram demonstrates the actual sequence of plastic hinge formula of structural loading to the ultimate failure. However, it is required to the bending moment diagram after each hinge deformation, which may not always convenient from a more direct, tough, not detailed calculation ultimate load capacity possible using the virtual work method. Assume the collapse mechanism is stress structure as the mention of the previous formulation. If system equilibrium substitute to virtual work displacement, and the virtual work done by the external forces is equal to the virtual work done by the internal forces. Okay, we have been shown here the external work, which is force into distance, and internal work into moment into rotation. So you must be keep in mind external work done equal to force into distance, and internal work moment into rotation. What is the this is the external work force into distance. The distance we have been shown here if we show here the simple supported beam P load is applied and L/2 so these are the maximum moment, and the deflection shake will be like this. These are the displacement delta. So delta will be here. Delta we can see tan theta, this is the theta and this is also theta. So tan theta equal to height into length, so height into length, so always height into length, theta equal to always height into length. So that's why we have been found here tan theta to 2l by l and theta equal to 12 by l. Why we are eliminating tan? Because tan is tan theta is very close to the theta because it is the very small. That's why theta equal to 12 by okay. Okay, we have been now we'll go to the here the internal external work, force into displacement, this is the force and this is the displacement, and internal work done into movement into rotation. Here is a movement and rotation, we have been no to rotation, but we are converting rotation to displacement. Rotation, that means uh, L/2 theta into L/2, theta into L/2 means 2l by theta. Here is the theta into L/2, that means 2l by theta, and finding here m equal to 4 theta by l. Now we can summarize external work done equal to internal work done, and putting this below p theta p delta equal to internal work m p equal to 4, and so m equal to 4 mp into l. Now we can see here another the load is p, so in external work p into displacement, this is the displacement, and internal work moment into rotation, mp equal to rotation 4 rotation. Why? Because we are doing the maximum moment. When we get the maximum moment, we have been seen here the 3 zone for getting the maximum moment. These are the zone 1 we have been seen in the left side and middle and right side. So that's why the structure will be hinge create will be this portion and this portion. We must be keep in mind the hinge will taking the rotation where the hinge is created. So that's why we are taking the 4 hinge, 1 2 3 4. So 4 theta is taken where the hinge is created. Okay, so 4 into theta, as we know, theta into L/2 or distance divided by 2, and finding this below. So external work done equal to internal work done, putting this below and finding here. Number 3 we've been shown here the internal external work done, force into distance, force equal to W into L, and distance here is the theta, here is not theta because theta by 2, as we have been shown here. Displacement, if we calculate like this, we have been here, so that displacement is 0 and here is the full displacement. So we are taking the average displacement 0 plus theta divided by 2. That's why we are taking theta divided by 2. And internal moment, internal work done, we know moment into rotation, and rotation into rotation, as we know in the right and left side, that's why to rotation. And theta equal to L/2, theta into L/2, delta into L/2. Okay, delta into L/2, and finding this value. So external work done equal to internal work done, and putting this below and finding this below. Now we have been seen the another is the number 4. I will calculate here in external work done equal to W into L into divided by 2, and internal work done finding this value. In the same way, we've been finding here internal work done equal to force into distance, as this is the UTL load, that's why delta by 2, and internal work done is MP equal to rotation. As we know, this is the 1 2 3. This is the rotation and funding this will be. And after taking this as the summation of d by d delta u into delta s and solving this equation and finding here 11.66 mp divided by L square. Okay, so now you can see some math example of material non-linearity plastic moment for beam and frames. These are the not material plastic moment, so this will be plastic and ultimate load, plastic hinge, okay. Now you can see the make the example of plastic hinge and ultimate load for frame beam and frame. Okay, let's start. Use the energy method to calculate the plastic moment MP needed to prevent the development of plastic hinge mechanism in the beam shown here. So it's been shown the AB and BC and CD. If we divide it here AB BC CD, it will be 11 W equal to 11 into 6 is MP divided by L square, and it will be 16 MP L square, and it will be N square. So if we drag this portion, then it will be like this. And for here W equal to 11.66 into MP L square and funding MP here. So BC portion, if we calculate BC, then it will be fixed support also, and it will be also fixed support. That's why toward the fixed support, and funding here MP equal to here. And last one we can see here CD, this portion, this right portion, and funding MP equal to 62. So these are the MP 42, 70 and 62. So you can see 70.31 keep. So we have 3 MP found in this structure. The capacity is required 70.31. Structure will be filled after structure will be collapsed after crossing 70.31 keep fit moment. Okay, so you keep in mind when calculate the load, so we'll take the maximum load and capacity, then take the moment. Okay, we've been seeing another math example. It's the reverse calculation. MB is given here and figure is given. So these are the AB member. So B member, we can say this is the fixed support. So these are the portion of AB. We can assume the B portion is fixed, and calculating here W and founding here the W. And another one BC portion, this is the BC portion, these are the fixed support we have assume, and founding W equal to 7.11. And last one we have been CD member, this is the fixed support, and founding P is 80. So 3. The capacity will be the capacity of the structure will be 7.11 K. So we can see the structure will be collapsed after 7.11 feet load. So when we calculate the load, when we take the load, then we take the minimum load. When we take the moment, they will take the maximum value. Okay, let's see another. Use the bending moment diagram of the beam is given here, ZIA and load shown in below P load to develop the plastic hinge mechanism and given on this below. So after finding this, this portion like cantilever, this is the cantilever. So ZI, this portion MP equal to PL by P into L, so P equal to 960. So this portion ZIU, so this portion we will know MP equal to PL by 8 and found 1920, and this portion we have been found MP equal to 960. So structure will be collapsed after 960. These are the here. Or we can use the bending moment diagram. So as we know here, the bending moment diagram will be like this. It will be 5P and it will be 5P. So bending moment, taking the moment is here. So after finding this MP equal to bending moment, as we know these are the MP, and the material, and we can see here the from MP, the section is given here a by 2 and x ay dy and d and MP equal to 14800. So these are the from bending moment, from bending moment diagram, MP equal to from bending moment diagram, and another from section, this section from material property, and found on P equal to 960. The structure will be collapsed after 960 load. Okay. So let's see another example. Calculate the distributed W load to needed to table of the plastic hinge mechanism of the beam ABC load rating shown. Number 1 by using the bending moment diagram. Number using energy formulation. Okay, we can see here the number 2, which is using bending moment diagram, as we've been drawing here bending moment diagram, taking the moment is here and RC found at summation of f of y and rb equal to found and x value found. For MP, as we know here, from section property, as we know MP equal to stress equal to a by 2 into d and found in 246, and we draw the bending moment diagram. From bending moment diagram, the maximum bending we have been found 22.1 into W, and MP we have been found from section property or material property, and found in W equal to 109.64 cubic feet. The structure will be collapsed after the crossing 109.64 cubic foot load. Now we can see the same diagram using energy formulation area. These are the diagram, and we draw the tentative diagram, a tentative bending moment diagram. We can show this will be maximum moment and this will be maximum moment. So we can assume that the structure will be failed either this portion or this portion, or we can say the maximum hinge create will be this point, either this point or this point. So first of all, I imagine the structure will be from the hinge will be created this portion. So that's why we have been taking the alpha is this portion. We can say the point B, and another portion we have been seeing the hinge will be created is here. So after, if we hinge is created here, the structure will be like this. That's why we have been drawn like this way. Okay. So so this is the failure mechanism shape 1, and this is shape 2, and this is the material. After the from material we have been found MP equal to containing this value and found in 203. But for shape 1 we have been found external work done equal to load into displacement. This is the load W into L, and displacement equal to delta into as this is the delta into delta by 2, as this is util load. That's why delta it will be delta by 2 as we are taking the average, and internal work done MP equal to alpha. This is the alpha, and alpha equal to d by L by 5. L means 5, deflection by 5, and deflection by length is given is 5, and putting and finding W value. And from shape 2, this is the shape 2, and same way external work done we've been found this way, and internal work done founding this way, and W equal to 9.22. So we've been found 16 and 9.22. The structure will be collapsed after crossing the 9.22 cubes. We can see the calculate the plastic moment MP needed to the prevent the plastic mechanism in the beam ABCD is given here, loaded and shown below by using energy method only. Okay, so we are using energy method. So as we've been seeing, this is the our diagram. So we draw the tentative moment diagram like this. So as when we complete drawing the tentative diagram, so you can say the plastic moment is here, or maximum moment will be 3 points. So you can say the hinge create will be 3 points. So first of all, we have been seeing the point B will be hinge create. Second one, we can say this point will be hinge create. So what will be happen if the hinge create is here? It will be like this. Okay. So the shape 1 diagram we have been seen here. The internal work done equal to force into deflection. The deflection is d by 2. Why d by delta by 2? Because this is the UDL load. That's why delta by 2. If the load is applied the point load, that will be the in that case that will be only delta. Okay. So we have been found 5 into delta, and internal work done equal to 4 mp equal to moment into rotation. The rotation will be shown alpha. Then alpha will be converted to the deflection, which is deflection divided by L, which is L is given the 5, and founding 25. In the shape 2, we have been taking the moment. As we know, the force into displacement, force is given here 10 kg, and displacement as delta, and delta divided by 2 as is the UDL load, and finding this below internal work done is found after comparing this and finding 33 2. So 25 and 33. So we'll take the maximum value for section constant. The beam will be collapsed after the crossing 32.5 cubic feet. The same way we use the energy method to calculate the plastic moment. Cause the necessary prevent the development mechanism in the shown below. We have been shown here. Now we will draw the tentative moment diagram like this way. So this is the maximum moment. That's why we are taking the plastic hinge will be created. This is the maximum moment. Plastic hinge will be created. If the plastic moment is created here, so section will be sagging like this way. And another one with the plastic moment is here. If the plastic moment is applied here, the diagram will be sagging like this. The last one is last thing. If the hinge is created here, the diagram will be like this. So this is the deflection shape 1, deflection shape 2, deflection shape 3. So from deflection shape 1, external work done, internal work done, and finding these below. From deflection shape 2, external work done, internal work done, and finding these below. And deflection shape 3, internal work done, external work done, finding these below. So the beam will be collapsed after the crossing 1875 cubic feet moment. So we have been finding the 3 value. One is 1645, another one is 1875, and last one we have been found 16.45. So we can say the beam will be collapsed after the crossing 1875 cubic feet moment. Okay. The same way we can use the energy method to calculate the plastic moment. The cross section necessary to prevent the development collapse mechanism is given here. So after the finding this value, after the finding this diagram, we will draw the tentative PMD diagram. I will draw like this way, as this support will be act the fixed support. That's why it will be sagging here, and this is the internal hinge. That's why the moment will be 0, and this is the moment also 0, the internal hinge, and here. So this we have been seeing the hinge will keep here and here, here. There will be hinge will be created here. Why? Because this is the maximum moment will be found in here. That's why the hinge will be created here. Okay, so the hinge is shape 1, shape 2, shape 3, shape 4, shape 5. So we are taking here the shape 1, external work done, internal work done. In the same way, shape 2, external work done, internal work done, shape 3, external work, internal work. and shape 4, shape 5, and this will be our last this will be our answer. We can see here another use the energy method to calculate the plastic moment of the cross section of the necessary prevent the development collapse mechanism of the given. Here we can see here after the finding this diagram, so the moment diagram will be like this. This is the tentative moment diagram, or you can see this is the maximum moment, and it will be also maximum moment, it will be also one moment, it will also. So at the maximum moment there will be hinge, this is the hinge, this is the hinge, and this is the hinge, and last one will be this is the hinge. So hinge will be created here. So from the shape 1 we've been taking the hinges here. So if we take the hinges here, the structure will be like this. These are the first shape, and taking the external work done equal to internal work done and finding this moment. The same case is we take the moment here. If we consider the internal hinge will be support, and what will be happen, it will be nothing, it will be act like this way. So this way. Another one, if we take the hinge is created here, then what will be happen, it will be act like this way. The same way this and this figure will be found based on the maximum moment and hinge location. Okay, from shape 3 we've been found external work done and internal work done and found the same plastic moment. And shape 4, shape 5, you can see here they use the bending moment diagram of the reinforced concrete beam. ABC is given, shown the calculate the concentrate payload and develop the plastic hinge mechanism. So all the data is given and finding this value P below. Okay, now we can see the energy method to calculate the plastic hinge zone. It will be from frame. Okay, so these are our diagram. This is the diagram, given diagram, and after finding this diagram we have been taking this as the hinge created will be like this way, and maximum moment will be here, as the diagram will be like this. That's why this, and while the considering the only frame, then it will be like this way. And the hinge created will be like this, and hinge created here. This is the fixed support, that's why the hinge created. If the column is not fixed support, then there will be no hinge will be created. Okay, so vertical load, from vertical load external work done equal to internal work done, and finding MP equal to this value. And these are the same, external work done, internal work done, and found MP 145. Okay, so structure will be collapse after the crossing 145 moment. Collapse will be failed before the failing the beam in this frame. Okay, we can see another use the energy method to calculate the plastic moment. Here is the pin support and this is the fixed support. And for the gravity load, the hinge will be created like this, and for lateral load the hinge created will be, there will be no hinge created because this is the pin support, there will be no moment is here. Here is the fixed support, it will be hinge created. Why? Because the huge movement will be created here. Okay, from this diagram we've been finding external work done and internal work done and moment 11, and from this lateral load we've been finding external work done, internal work done, and moment will be 97. So structure will be collapsed after the crossing 97.97 cubic feet moment. Here's the another example, use the energy method to calculate the plastic moment. Here's the 58. and these are the fixed support, and this is the pin support. For gravity load, the phenomena will be like this. For lateral load, there will be no hinge, but here will be hinge, and these are the same. For gravity load, we have been found moment 11, but when the lateral load, we have been found 207. In the previous case, the same thing we have been found the 10 feet but 58, and here we have been found 97. But in this case, here the 17 length in 17, here the length in 9, and found 207. Here we can say that this is the double of the 97 almost. So the frame will be collapsed after the crossing 207 cubic feet. Use the energy method to calculate the load P in the load mechanism given all the data. Finding this for vertical load. For vertical load, this is the gravity load. MP equal to 106 and 8.33. Use the yield moment and plastic moment capacity of the section below. In more the elastic fully plastic material is given here. We've been taking the A below, A by 2 X D and D2, and D will be 5.74, and the CG moment of inertia my equal to 1074 and MP equal to 3837. So plastic moment is always greater than the yielding moment. Use the energy method to calculate the plastic moment needed to prevent the development plastic load mechanism from is given here. For gravity load, for lateral load, for gravity load to have been vertical load, found in external work done, internal work done, and MP equal to 15. For lateral load, we have been found external work done, internal work done, and MP equal to 75. So we use the calculate the yield moment MI and plastic moment. The capacity section is given in fully elastic plastic. So A is found here, A by 2 X D Y bar and H minus Y bar moment of inertia, and My equal to found 15205 and MP equal to 26222. So MP is greater than Mi, so it is okay. Here the another example in the frame ABCD is loaded and shown the energy method to calculate the plastic moment required to prevent the formulation of the beam mechanism BCN side sway mechanism of the frame. Also calculate required the yield strength of the elastoplastic material. So column size is 15 into 20 and beam is 10 into 20. The load is given here. This is the gravity load. This is the lateral load. So vertical load or gravity load, we have been found external work done and internal work done, and found MP equal to 15, and MP is given here, so minus 60. For lateral or horizontal load, external work done, internal work done, MP equal to 100. We know MP is for 100 and founding stress equal to 144. Okay. Use the energy. Now we can see another one. Use the energy method to calculate the plastic moment is needed to prevent the development plastic hinge mechanism in the beam is given here. So you can see here after the getting here, we will draw the tentative moment diagram like this. So the maximum, where the maximum moment, there will be hinge will be created like this way. So you can see the shape, deflection shape 1, shape 2 and shape 3. So after finding deflection shape 1 to 3, for deflection shape 1, external work done, internal work done, MP equal to 40. From deflection shape 2, external work done, internal work done, and found MP equal to 100, so it will be increased. So shape 3, external work done, internal work done, and MP equal to 24, so it will be reduced. So we can see the beam will be collapsed after the crossing 100 cubic feet moment. You can see another energy method to calculate the plastic moment capacity of the building here 73, 69, 58. And for here lateral load, this is a gravity load. For lateral load, the diagram will be like this. From gravity load or particle load, the diagram will be like this. So after putting lateral load is the plastic moment 803, and the gravity load will be from 109 192.5. Okay everyone, thank you. If you have any question, then let me know. Thank you everyone for your patience. These are the ended. Before going to here, I just want to say this is the one part and last part is here, the plastic hinge and ultimate load capacity. This is the plastic moment and ultimate load capacity. This is the very important.